Hello everyone, welcome to V2 Exam Topics YouTube channel. Today we will discuss from the fourth unit. The topic name is starting and speed control of induction motor. How we will start the induction motor and what are the speed control methods. We will go through with these two topics today. Now you can observe basically the three-phase induction motor is a self-started motor. Even though we use starting methods, the three-phase induction motor, which when connected to three-phase supply, it's create rotating magnetic field. We already well know about this. This will link further rotator conductors which in will induce the a current. The rotor conductors that create the rotating magnetic field. This magnetic field created by the rotor will interact with the rotor magnetic field and the stator and produce the rotating. Therefore, the three-phase induction motor employed a starting method not to provide starting torque in the rotor, but because of the following reasons. Mainly, there are two reasons. One is reduced heavy starting currents. We already well known about this. When you on the any motor, it will take huge amount of current to prevent this motor from overheating. And the second one is providing the overload and no load protection also. Different starting methods are employed for the starting of induction motor to prevent damage to the winding due to high starting torques. The starting method should be also ensure that the starting torque of the motor at least 50% to the 100% more than the expected load torque, so that the motor will reach the desired speed in a reasonable short time. Some of the common starting methods. Now observe, this is very important. What are the important starting methods are there? First one is direct online starter. You can directly connect it supply to the machine. And second one is star to delta starter. We can change the star connection to delta connection starter while changing the triple pole switch. And third one is auto transformer starter. And fourth one is stator resistance starter. Last one is rotor resistance starter. Now we will see these five types. Now, if you observe the first method, direct online starter. The direct online starter is the simplest and most inexpensive of all starting methods, usually used for the squirrel gauge induction motor. It is directly connected to the contacts of the motor to fulfill supply. Directly it is connected to the full supply voltage. So, shows the circuit diagram, direct online starter. It consisting of coil operated C controlled by starter and stop push button. If you observe this, in this we can observe this is a the C coil, it pulls to start and then stop. And the process of starting button S1, which normally opened by the spring, and the contact coil C energized from the two line contact R and Y. The three main contacts. M is auxiliary contact A closed and the terminals A and B short circuited. The motor is connected to the supply. When the pressure on the S1 is you realize to move the back under the spring action. Even then the coil C remains energized through AB. Thus main contact M remains closed and the motor continues to get supply. When the stop push button S2, which is normally helpful to close the pressure. The supplies through contact M disconnect since the coil is de-energized the main contact M. Auxiliary contact A are open. Supply the motor, disconnect and the motor stops. Observe this connection. We want to start the motor, we have to pull this start button. The three lines of supply is directly connected to the motor. It will use it to give the supply to the motor. If you want to stop this, you can use this S2 switch. In case of no load voltage or over voltage, the coil will energize, it will trip by this coil. From this, we can protect the motor from two conditions. One is overload protection, another one is under voltage protection. We can go through these two. And coming to the important topic, the starting, the relation between the starting and full load torque in case of direct online connection. We already well known about rotor output P2 is equal to 2 pi ns 60 into T. We know T is equal power by omega s. You can simply write that is equal to, we can replace this, but rotor copper losses is equal to S into P2 times. This is equal to 3 I2 R square R22 into S into P2. We can write P2 is equal to 3 R2 square and R2 by S. Now we can simply say that the torque is directly proportional to the rotor current and inversely proportional to the slip. It is for, in case of starting, we know S is equal to 1. If you substitute S is equal to 1, you will get this equation. Now divided by both two equation, finally you will get the starting torque and full load torque relation is equal I starting by I full load whole square into SF square. It is very helpful formula. But from this we can determine the starting torque and full load torque. It is the relation for only direct online starter. Now there are some advantages and disadvantages. You can go through with this slide. You can take a screenshot, make a note. Now coming to the second one, star delta starter connection. Generally we know, in case of star connection, line current and phase currents are same. Now we can observe, in case of star connection, the line current and phase currents are same, but in case of delta connection, the line current is 3 times of phase current, root 3 times of phase current. In this method, the voltage will be reduced by VL by root 3 times and the current will increases for the stator side. Now observe this connection. By using this type of connection, we use triple pole double throw. Triple pole double throw. Here one is one throw and here also another throw. And we have triple poles. One, two, three. Triple poles. First it is connected in star connection. And and then we can change into the delta connection where the starting only. Observe this. A dash, B dash, C dash. If you connect all starting points at one point, take the remaining, it is act as a star connection. If you connect starting point and ending point and starting point of another winding, we call it as delta connection. Now we can observe the relation between the starting and full load torque. In case of star to delta connection, we can see this. First it acts as a star connection and then it will go through the delta connection. Now the main relation between the starting torque and full load torque. From the above equations, we can write I starting is equal to V by root 3 times of Z from Ohm's law only. Then I starting is equal to 1 by root 3 times of I starting current. This is, we can simply substitute IST by IF is equal to IS starting current by full load current whole square into SF. Then we know I full load current is equal to root 3 times of IF. Then we can simply write 1 by 3 times. Now we can observe here, when starting and full load currents are same, I starting torque is equal nearly 3 times of I full load current, I full load torque into SF. Now we can go through the advantages of star delta starter connection. The main advantages is there is a relatively low price and number of times they can operate at. Components required is very little space. The starter current is reduced approximately 1 by third time. Now coming to third type of starter, that is auto transformer starter. By using auto transformer starter, we can adjust the starting current 1 by root 3 times. Now you can see this. This is three phase auto transformer. In this we have variac. We can vary the starting supply voltage by using this variac. It is a three-phase auto transformer connection given to the star connection starter. We can derive the relation between the starting torque and full load torque. It is also similar like the previous one. Here we have to take the K value. K is a auto transformer turns ratio. In exam, if they given K value 1 by root 3, you will get here 1 by 3. it because of 1 by root 3 square is equal to 1 by 3. The sum of the advantages of auto transformer and disadvantages of auto transformer. It is a great efficiency. Only one winding is required. A required voltage can be tapped off at the required turns. Taps on the transformer allow adjust to starting torque to meet the particular requirements. Now coming to the fourth, stator resistance starter. It is similar like your DC starting method. We can directly add the resistance to the stator side. Observe this. These are resistors added to the stator side. Now coming to the relation between the starting torque and full load torque is equal to x square times of ISC by IF whole square. The x is a variable of how much starting current is equal to ISC current, short circuit current. Now the we left with only one starting method, that is rotor resistance starter. Now in this case we can directly add the starting. At the starting, we can connect the variable resistor to the rotor side. It is only applicable to slip ring induction motor. In this method, when you add the extra resistance, the starting current can be reduced due to this resistance effect to draw less current in case of starting. If you want, you can go through this problem. Here, the starting torque and full load torque is equal to 1 by 3 times of ISA and slip at full load. The start to delta connection, we already have 1 by 3 times the starting current. Then we can observe the relation for the starting and full load torque is equal to 0.714. It means if the full load torque is 1, the starting torque is equal to 0.417. And similarly, in case of auto transformer also, if you take tapping value turns ratio 1 by 2, then you will get the 0.3125 times. Now we go with the now we will discuss speed control of three-phase induction motor. Generally, we can control the speed by using this formula. We already well know S is equal ns minus nr by ns. Here we can write nr is equal ns into 1 minus s. If you change the ns, the speed also varies, and we can change by using s also. We already well known ns is equal 120 f by p. And from the torque equation, if you vary this supply voltage, we can vary the torque. If you vary this x2 value and rotor resistor, also we can vary the torque. If the torque vary, the speed also vary. Now coming to the speed control methods of three-phase induction motor, further classified into from the stator side. First one is V by F control or frequency control. Second one is controlling supply voltage. Controlling supply voltage, that is nothing but a supply voltage Vs, and the changing the number of stator poles. We know Ns is equal to 120 F by P. If you vary this P value, automatically slip also varies. Adding rheostat in the stator circuit. If you add the extra resistance to the stator side, the current will flow is less, then the speed will vary. Next, speed control of the three-phase induction motor from the rotor side also further classified into adding the extra resistance to the rotor side and the cascade control method. We can connect another motor, and the last one is injected slip frequency EMF into the rotor side. Now we can observe speed control from the stator side. First one is V by F control or frequency control. In this, we are well and aware of this. Ns is equal to 120 F by P. If the frequency increases, the speed also increases. If the frequency decreases, the speed also decreases. Now, from the EMF equation in the induction motor and transformer, we can know E is equal to induced EMF is directly proportional to the frequency and flux. For that purpose, we can write phi m is equal to V by Kt into F. Here, K is nothing but a winding constant, T is nothing but a number of turns. Simply, we can write phi m is equal to V by F. If you kept this constant, flux is also constant. The flux constant, we can directly vary the frequency, then speed will varies depending upon frequency. How control this V by F method means by varying the by using the converter and inverter set. Here the main point is if you kept V by F constant, only frequency will vary, the speed will vary. Now second point, the second controlling method is controlling supply voltage. From the torque equation we know T is directly proportional to the E2 square. We are already aware of this equation. Now if I vary the supply frequency, the torque is varies two times, two square times. For example, if the supply voltage is increases by two times, the torque is increases to four times. From this method, speed control is rarely used because a small change in speed is required, large reducing in the supply. Hence, the current drawn from the motor is increases, which causes the overheating. Why? Because if you vary the supply voltage double, then torque is increases to around four times. Now, changing the number of stator poles. In this method, speed control by the pole changing are suitable for the cage motor only because of the cage rotor automatically develops a number of poles usually depending upon stator winding. In this method, the stator is provided with the two separated windings. For example, for the different poles of numbers, I am taking 6 pole, 4 pole machine. For the 50 Hz supply, for the 6 pole you will get 1000 rpm. For the pole you will get 1500 rpm. For the slip of 5% you may get 950 rpm and second one is 460 rpm. Why? Because if the change the stator poles count automatically rotor will changes in case of only squirrel gauge. In case of only squirrel gauge. Why? Because squirrel gauge rotor can change its poles with respect to the stator. Next one is adding rheostat in the stator circuit. That is nothing but a T is directly proportional to SV square. This method, speed of three-phase induction motor rheostat is added resistor circuit which voltage set drops. In this case, if the voltages get dropped, the torque will also get dropped. We de- decreases the supply voltage, torque will be decreased. But for the supplying the same load, the torque must be remain the same. It is possible if we increase the slip. If slip is increases, motor runs with reducing speed. We are well aware of this. Next, coming to the second methods. Those are nothing but a speed control from the rotor side. Adding the external resistance on the rotor side. We know torque equation. If the resistor is added extra, then the torque will decreases. Now, in increasing the rotor resistance, the T2 torque decreases, but the supply the same load. Torque must be remains constant. So we increase the slip, which will further result in the decreasing the rotor speed. Decreasing the rotor speed. Thus, by adding additional resistance on rotor side, we can decrease the speed and three-phase induction motor. Try to observe this main point. If I increase the resistor, even though the torque should be constant, for that purpose, the slip is also increases. If the slip increases, automatically the speed is decreases. Now I hope you understood this method. And second method is cascade control method. In this we can directly connect the extra motor. It is a main motor, our motor, it is auxiliary motor, extra motor. The slip power is sent to the auxiliary motor. Now in this type of connection we have to take poles of the auxiliary motor and main motor. That will affect the speed. Now we can observe here the given synchronous speed ns is equal to 120f by pa plus pf. We can use differentially connected. In that case, we may write 120f by pm minus pa. We can vary the speed by using connection. How we are connecting? Whether we are connecting differentially cascade or opposite directionally connected. From above connection, we can get the main speed supply Pm and the auxiliary speed supply by Pa, and two cumulative connection Pm minus Pa, and last connection is Pm minus Pa. We will get these four types of speed connections. The method is rarely used because of too much of expense. We have to use another motor. Now coming to the last one, injected supply frequency EMF into the rotor side. If you inject the EMF from the rotor side, from the rotor side, this type of speed control induction motor done by adding extra resistance circuit, some part of the power is called slip power, that is also called as last IA squared. Therefore, the efficiency of three-phase induction motor is reduced by this method of speed control. This slip power loss can be recalled by using supply back in order to improve the overall efficiency of the three-phase induction motor. The scheme is recovering of the power is called slip power recovery scheme. The basic principle of slip power recovery is to connect an external source of EMF slip frequency to the rotor side. The injected EMF either oppose a rotor injected EMF and adding the rotor EMF here. EMF. If we opposes the induced EMF, the rotor resistance increases, hence the speed is decreases. If the injected EMF is adding when moving for a point, the total resistance is decreases and the speed is increases. Therefore, by injecting and reducing EMF is the circuit speed can control by using EMF, by using this type of injection EMF to the rotor side. Now coming to the last thing, application of three-phase induction motor. We already studied the classification difference between the squirrel cage induction motor and slip ring induction motor. For the loads required low starting torque and nearly constant speed, the squirrel cage induction motors are best choice. The squirrel cage induction motors may be designed with low rotor resistors or with high rotor resistors. Squirrel cage motor with low resistors are used for the fans, centrifugal pumps, woodworking tools. The squirrel gauge motor with high rotor resistance are used for the compressors, reciprocating pumps, and punching machines, shears, and elevators. Now coming to application of slip ring induction, these are most used for the high starting torque and for the high accurate speed control. Hence, this such of motors is used for the hose, cranes, lifts, driving lines, shafts, and pumps, winding machines, mills, etc. I hope you understood this topic, how many starting methods and how the speed can be controlled. We have to remember the main equation for the speed control. Torque is directly proportional to S square by E square by R2 square S x2 whole square. If you want to write S. And if you maintain a constant torque, we have to vary either rotor resistance, then the slip is also increases. We should maintain a constant torque, then the speed is directly proportional to 1 minus s of ns. I hope you understood this topic. Thanks for watching.